Hi guys, in today's video we're going to talk about the complexity class p-poly and the idea of a sparse language, and a term called single group, a sparse language with additional mutations. But before getting into the action, let's match our expectations. My videos depend on the wisdom of the crowd, a topic that really fascinates me. Since I'm studying this topic by myself, there might be an occasional mistake in what I say. Please let me know in the comment section below if you wish to correct me, of course. I promise to read all comments and re-upload if necessary. Together, we can answer tough questions in a better way. Also, please subscribe to my channel. I tend to upload many videos on this topic. Let's jump right into it. Alright, sparse language. Notice that given a language that contains only strings of the length of n on a binary alphabet, there are exponential possibilities for words in that language, 2 to the power of n words to be precise. If no additional limitations apply, of course, such that every second letter must be the letter 0, for example. A sparse language contains a polynomial number of words out of the exponential possibilities. The formal definition for sparse is the following. Set S subset or equal to 0, 1 clean star called sparse if there is a polynomial p for any n, the size of the conjunction between the set S and 0, 1 with n appearances is bounded under the polynomial Pn. Single group. A single group is a made-up term which is somewhat similar to a sparse language. We would say that S subset or equal to 0, 1 clean star is a single group if for any n the size of the conjunction of S with 0, 1 with n appearances is lesser or equal to 1. P-poly. We would now prove that S in P-poly if and only if there is a Cook reduction, also known as polynomial Turing reduction from S to a single group. First direction. Assume that S in P-poly. We will see that there is a Cook reduction from S to a single group. We know that S is in p-poly if and only if there is a Cook reduction from S to a sparse group. Our difficulty arises from the additional limitation of a single group. While the conjunction between S and the sparse group is bounded by a poly, the conjunction between S and the single group is bounded by 1. To achieve that, we would build the single group in such a way that we would have one word of each length at most. A single group must fulfill 2 properties. Its conjunction with S must be of the size of 1 at most. 2. It must be a good alternative to a sparse group. Help us determine S in a polynomial computation time. We would now spend a moment build this group. The first idea that might come to our mind is to include the advices as the single group. Since every length of input has a unique advice by definition, we would fulfill the first condition. But in regards determine S in a poly time, it is difficult to see how such a group helps us. Trying to solve the problem with the lack of fulfillment of the second condition, the first intuition may come to our mind is to unfold each advice to its prefix. For example, if we have the word 100, we would unfold it to 1, 10, and 100. The problem we have, however, with such an idea is that every word except the empty word has a prefix of the length of 1, so we cannot enforce the first condition of having a word of each length once at most. To overcome this issue, we would have to understand the pattern we have in hand. An advice of the length of 3, for example, unfolds to 3 different words. If we follow our intuition, an advice of the length of 4 unfolds to 4 different words. Each represents a prefix of the original word from a length of 1 to 4. Since we have one advice of each length, we can take advantage of this idea. How? We would add in front of each word special unreadable characters of an amount equal to the longest word representing the previous advice. Let us see an example. So this is the example, and what we are seeing here, the numbers in the center represent the length of the new words according to our build. the numbers in the most left represent the original devices. The cells and crosses in the right represent the way new words would look like. An empty cell represents a special unreadable character, while X represents a bit, either 1 or 0. Because every word is longer than its predecessor, we would enforce the first condition. Now, after we understood how the single group will look like, we can finally prove the direction. As a reminder, we assume that S is in p-poly, therefore we know that there is a Cook reduction from S to a sparse group. We are required to prove that there is a Cook reduction to a single group. We would notate the Turing machine that determined the Cook reduction from S to the sparse group with M1. We would define Turing machine M2, which behaves exactly as M1, except that the oracle that asked membership questions to the sparse group would now ask membership questions the single group. We would notice that if we filter the unreadable characters, we end up with an identical group to the sparse group. And we already know that we have a Cook reduction from S to the sparse group. Therefore, we successfully solved the challenges related to the restrictions with single group, and we proved that direction. Second direction. Assume that there is a Cook reduction from S to a single group. We would see that S is in p-poly. If there is a Cook reduction from S to a single group, then there is a Cook reduction from S to a sparse group, since any single group is a sparse group with additional properties. Therefore, S is in p-poly as required. In conclusion, we had seen that S is in p-poly if and only if there is a Cook reduction from S to a single group, as required. Well, that's about it. I hope you learned something new from this video, and please comment below with your thoughts. First degree studies in university are all about social studies, and this project comes to encourage that. Please subscribe to my channel. Until next time, good luck.